this tutorial, we will highlight Jaguar pKa, a computational package that predicts pKa's of molecular systems on the basis of density functional theory calculations performed by the program Jaguar. Now, whether you have a drug-like molecule, such as the structure of alpha protein shown here, or a dye, such as the structure of this chromophore, or something more exotic, like this silicon-based molecule, Jaguar pKa will work on it. Owing to an innovative technology called the shell model, Jaguar pKa is able to work with any functional group, even if specific parameterization for it might be unavailable. Now, before we proceed, you can find out more details about the Jaguar pKa module, including the theory and methodology, in the Jaguar user manual. Just head up to Help, Manual Index, Jaguar user manual, then find the pKa prediction module, which for Jaguar version 8 is in chapter 13. Okay, so in this tutorial we'll run Jaguar pKa on 3 structures. The first example we'll use is the structure of alpha protein, which will represent our drug-like molecule, with the pKa atom in question being the amine on the piperidine ring shown here. Okay, so let's run Jaguar pKa. If you're using Maestro, just go to Applications, Jaguar pKa. Or if you're in the task view mode, just go to Tasks, pKa Prediction, Quantum Mechanical. And an even quicker way to use in future is to just type pKa over here in the task tree. Now, if you're using Maestro Material Science, you'll want to go to Tasks, Quantum Mechanics, pKa. Okay, once the panel is open, we'll use the structure from the workspace. We'll use the default molecular states, and we'll pick the pKa atom. Now, the pKa atom should be the acidic hydrogen in an acid or the basic atom in a base. Now, you can use the conjugate acid or conjugate base as inputs, but you should choose the hydrogen from the conjugate acid or the heavy atom for the conjugate base. So in our example of alpha protein shown here, I can pick the hydrogen, like so, or had I built the deprotonated state, I would then pick the nitrogen. It doesn't matter here, as we should get the same answer for this pKa system. Now next we'll check on Perform Conformational Searches, as this will run a conformational search using Macromodel to select the optimal conformer before performing the pKa calculation. We'll keep the default settings under the SCF and the solvent tabs, which is using water. Again, more details can be found in the Jaguar user manual. We can then go back and name the job, and then we'll click Run to start. Now, depending on the size of the molecule and the options you've selected, jobs can run for a few minutes to a few hours. So while this job is running, we can repeat the process for the other examples. Now, this chromophore molecule is another good example because it can be modeled as either an acid or a base. For example, if we open the 2D Sketcher tool on the toolbar, we can clearly see that a pKa atom could be this hydrogen on the hydroxyl group that will deprotonate, like an acid, or a proton can attach here to this nitrogen, like a base, which would be the other pKa atom. So because we'll be performing calculations using 2 pKa atoms, we can just duplicate this molecule and rename it based on the pKa atom that we'll pick. So let's just right-click on the title on the entry list, and then choose Duplicate in Place. Then we can single-click to rename it. In this case, I'll just append the pKa atom to remind me which is which. Okay, so now we'll run Jaguar pKa again. This time we'll choose the hydrogen on the hydroxyl group, and we'll keep the same settings, but we'll rename the job. And now for the other entry, we'll choose the nitrogen as our new pKa atom. And now while those jobs are running, we can also run our silicon-based example of a more exotic molecule, just to see how well Jaguar pKa performs. Okay, when the jobs are finished, we can review the results over in the project table. Now notice that I've already added the experimental results manually, just so we can compare the values. However, it looks like the properties are not shown automatically in my table, so I'll just click Show Family and choose Jaguar All. So if we compare the experimental and predicted pKa values, we can see that we came pretty close, which certainly highlights the accuracy of Jaguar pKa. Now, in the case of alpha protein, with a predicted pKa of 8.6, which is close to 8.7, the experimental result, we can probably assume that the tertiary nitrogen on the piperidine ring is going to be protonated in water, and maybe even so at physiological pH. Now, in the case of the chromophore molecule, using the predicted values, which are in line with experiment, we can imagine that as we add base, the most acidic proton will be removed first from the nitrogen, which has the lower pKa, followed by the hydroxyl group, which has a higher pKa value. And finally, we can see with the silicon base example that Jaguar pKa is able to work on more exotic molecules, and in this case get good results, even though parameterization for specific functional groups might be unavailable.